This is lecture 5 of machine learning, and in this lecture, we are going to discuss a concluding model optimization technique which is based on model validation. So, as you have overseen in previous few lectures, that whenever we are tackling a machine learning task, the first and foremost element of a machine learning task is to comprehend the problem. And once you have got to know about the problem, the next phase is to get the data and clean it. After data preparation, you choose a model to train it. And during the model training, you test different hypotheses to formulate your problem more specifically. So once you have formulated the problem, you use different optimization techniques to fit your model more appropriately with respect to your data examples. And we discussed quite a few techniques in the previous lectures to optimize your model with respect to your data examples. The next task is to test your model on the unseen dataset. This will give a accurate quality prediction of your model, that how accurate your model will predict on the upcoming data. So, so in this lecture we are going to overview a machine learning methodology once again, and we will start by picking a model. However, in this lecture we will focus on the validation of the model instead of optimization techniques. So there are two common problems occur while you generalize your model after training and testing on the validation or testing set. The common problem is overfitting and underfitting of the model. So it is a broad spectrum discussion of the overfitting and underfitting, but in this lecture I will provide you certain guidelines to overcome overfitting and underfitting. So one of the techniques for model validation is used called cross validation. So there are various methods to use cross validation techniques, and finally you pick again the model depending upon the techniques which perform better using the cross validation. So if you recall, the typical machine learning task was to learn from the examples. That means you feed the training examples to a machine learning algorithm. The algorithm will adapt its parameters with respect to the training examples so that it accurately predicts on the training data. So once the algorithm is trained on the training data, it can be used to predict on the testing data, and then if it generalizes to an acceptable quality, you can use it in the practical settings, or you can further feed the input to another model. So unless the set of pre-classified examples, or in the case of regression examples, if the data is not really big enough, the results will be unreliable because the smaller data set will not represent the overall phenomena which can be captured by collecting all of the related examples with respect to that particular phenomena. And in this case, if you have a smaller set of examples, your model will not generalize appropriately. So there is another problem, which is that some parameters are non-tunable. So a parameter, for example, let's say is said to be non-tunable if tuning or training it on the training data leads to overfitting. That means if your parameter is unable to learn the examples by accurate prediction, or if it learns too much, that means your parameter is unable to train more. For example, if you choose a random value of k in the k nearest neighbors and you reach a point where k is too minimum or too large so that it is unable to predict correctly and it classify each example to its own class. Or for example, you can have different number of units in a neural network. So if you have more neural network layers, there are chances that if you have fewer data examples, your model will likely overfit. Therefore, to overcome these problems, specific methodologies of repeated trials are used, and you can employ a random subsampling technique in which you can randomly pick a data and train your algorithm on that particular data. Or alternatively, you can use a KFold cross-validation technique in which you divide the training examples to a number of sets and use the sets to training and testing respectively. So there are various techniques to use these examples or these trial techniques. A common strategy is to implement the stratified versions of any of the technique, or you can use a 5 cross 2 cross validation. So these are just two variants of the first two techniques, and you can mix and match of all of these four techniques to apply to your learning algorithms. So the code examples provided in the previous few lectures, and particularly with this lecture, deals with the problems of cross validation and stratified versions of these cross validations. So the first technique we have is the random subsampling. So for example, let's say you have the set of pre-classified, or in terms of regression, you have set of pre-known examples where the target labels are known. So in the case of random sampling, you just have to divide the set randomly into training and testing examples. So there is no predefined criteria that which example will be will belong to the training set and which example will belong to the testing set. So you choose a random criteria, and then based on this random criteria you induce the training model from the training set. That means training data is used to fit model parameters. K is the case for in KNN, or you can use other parameters such as leaf depth in case of Decision trees, or depth of the nodes. So once you have trained your model, you evaluate the trained model onto the onto the testing set this time. So you had division of two models, training model and the testing model. That is the representation of the actual examples into the testing set and the training set. So again, if uh, I will put a certain emphasis in that you always train your machine learning algorithm onto the training set, and once you have trained the algorithm, you evaluate this trained algorithm onto the testing set. So in this case, test data is used to assess how trained model generalizes to the new data, and you can repeat this step to a number of times, and then you calculate the average error rate over the training examples and the number of cycles, and then you report this error as a generalization error. So if your generalization error limits itself to a certain threshold, you proceed with the model evaluation to its deployment phase. So selection of a model is a critical aspect towards the success of your machine learning project. So for example, We want to fix a polynomial machine algorithm for the provided data in blue dots. The blue dots represent the training example. So instead of training a polynomial function, we take another parameter which is the degree of the polynomial, and we make it the hyperparameter of the function, and it is represented as d. So our learning machine will be a function which is a component of or the evaluation of the input feature vectors x, the amount of weight applied w, and the number of the polynomial degree. So let's say for this case we picked three models, and depending upon the degree of the polynomial. So in the first case we chose degree 1. That means it will be a linear model. So the linear model is represented in red line here. So as you can see, there are so many errors that this training trained model does not fit to the training example. So let's say we increase the degree of our training algorithm, and we trained another algorithm into onto the same data set, and this case is represented with a green line. So again you can see this model implemented in the on the same data set, and it uh, classifies or predicts three examples out of four correctly. So there is one error. So if we increase degree to degree of the polynomial to 3, so we can see the algorithm represented in yellow line correctly maps to all of the four applications. So you generalize it to the unseen data. So before the generalization, you measure the training error. So in this case, you have seen there was enormous error on the first case because the training algorithm was unable to classify or predict any of the examples. So in the second case, you can see the training error is 1 out of 4, and in the third case, you can see the training error is 0 out of 4. So training error uh, is one of a parameter to classify the accuracy or the goodness of your model, but it is not the ultimate criteria. So for example, in this case, we can see the training error is a bad measure to choose the degree of the polynomial. As we can see, the degree 3 is the best according to the training error, but it can overfit the data. That means maybe this example is a noise and we are over complexing the model to model itself to these noises as well. Therefore, there are high probability that this will result to an overfitting model. So let's generalize this model, and for the generalization we have to use this model onto the testing examples to check its correctness. And for this case, the testing examples are marked as cross in the hyperplane. Therefore, we predicted the error for each of the models presented in the previous slide. So as you can see, there is a higher value of error in the first degree model, and there is also a significant error onto the third degree level because the degree of the or the complexity of the model was quite far above than the training data it represented, and we can see there is a significantly lower value of the error in degree polynomial 2. So what about the test error if we choose it for the measurement of the quality of our prediction or the quality of our model? It seems more appropriate. So as you can see that degree 2 is the best model according to the test error, which is based on the dataset provided in the previous slide. So except this error, what do we have to report as well? So here the condition must be checked that test error should be computed on the data that was not used for training at all. So in this case, we have to mention that the test data here is used for training is particularly for choosing the model or for choosing one of the model trained on the multiple training datasets. So which will give us an optimum score or the best score from each of the trained model, and we will pick the best model with the lowest generalization error, or the which model predicts accurate examples on the testing dataset. So now there are two conflicting situations we have come around. For example, let's say a model that performs very well onto the training examples but does not perform equally well onto the test examples is considered a less probable choice for optimal decision. However, there can be cases where a model that has performed badly on to the training examples but good predictions on to the test examples may increase its score for the selection as an optimal model. So this may be the case because testing example data are more similar to the trained model, therefore we may have the ambiguity of the result. So same question can be asked when choosing among several models. In our case of polynomial degree example can be looked at choosing among three models, for example degree 1, 2 or 3. To overcome this problem, another solution is presented in the literature, which is splitting the data into three parts: the training examples, the test examples, and another set for validation examples. So again, the task for the machine learning algorithm is to train onto the training example and tune parameters with respect to weights on these training examples. The next task is to validate the model onto the validation dataset. That means training or fine-tuning the parameters to select the best model among which performed better on the training set, and then choosing the best which performed onto the validation set. And once you have fine-tuned your model onto the validation set, then you use the test set to assess the final performance. And among those who were qualified as best models among the validation set are used to predict onto the test set, and among those the models which perform better onto the test data are chosen as an optimal models. So again you have to measure three errors in this case: the training error which is computed onto the training example, validation error computed onto the validation example, and finally the generalization error or the test error computing on the test examples. So deviation is not necessarily 60-20 or 20. You can employ different set of or different proportions of deviance with respect to the amount of data available to you. But for smaller data sets, this is a good division to choose. So incorporating another part of datasets will divide the datasets into three sets, namely training, validation, and test data. So we use the previous example with the same three algorithms to train on to the training data, and we measure the training error. And these models are again fed to another subset of the example, which is the validation dataset, and you measure the validation error on the examples using the three models we have been using so far. So as you can see, for the typical case, the validation error is reported for three different models. So again, we can see the validation error is slightly on the lower side in the degree 2 polynomial classifier. Therefore, degree 2 polynomial classifier is an optimal decision to choose. And then we measure this uh, model onto the test example for generalization errors, and let's say for the generalization error we have computed a test error of 1.3. Therefore we have an optimal decision for this particular dataset to choose this particular algorithm. So whenever you are modeling a data set with a model, you will encounter a situation where you see a training error is not going downwards. So you will try to improve the or enhance the complexity of model so that you reduced onto the training error. This is particularly you want to learn the all of the aspects or insights from the data. Therefore, you will like to reduce the training error. But as with the number of base function or the number of features increase, your training error is likely to decrease because it will more it will be more able for a training algorithm to model the datasets with complex parameters. But when you check it onto the validation dataset, there are chances that if you have increased the complexity level to a higher value than the representative datasets, there are uh, there are significant chances that your validation error will not behave similarly like the training error. Therefore, complex models, in the terms of complex model, we say the complex models then the datasets are more likely to have a higher validation error. That means the model is not a correct representation of the data, rather it is a complex function which is also mapping the noise as a function itself. Therefore, when it sees the validation example with a lower amount of noise, it is likely to uh, perform ill-manneredly. So for example, you need to choose a number of hidden units in a multi-layer neural network, and if you increase the number of units, you can fit the better model with respect to the training data. But at the same point, you will overfit the data if you are increasing the number of hidden units to an acceptable level. And when you pass that acceptable level, there are more chances that your validation error is likely to increase. So the generalization error usually expressed in the sum of three very different errors, and this is called the bias variance trade-off. So bias and variance are the characteristics of the model, Bias error bias is an assumption of the model. If you have a linear example, for example, we have been using a linear method which is wx plus b. So any assumption you make with respect to your data is the bias term. On the other hand, variance is the minute sensitivity with respect to your model parameters. So the bias term or the bias factor of the generalization error is due to the wrong assumption you make with respect to your data, such as assuming that data is linear. However, it is actually quadratic. So this is the wrong assumption. So if you have a high bias model, it is more likely that it will underfit the training data. That means you are unable to capture the assumptions of training data. Therefore, you will have a high bias and it will be an underfitting of the model. On the other hand, the variance part is due to the model's excessive sensitivity to the small variations in the training data. A model with many degrees of freedom, such as a high degree polynomial model, is likely to have high variance and therefore it will overfit the training data. So in simple terms, if you have a simpler model, the bias will be high and it will have underfitting of the data. On the other hand, if you have a high variance, your model is sensitive to even noise as well. Therefore, it will have overfitting problem. So apart from these two errors, there is another kind of error which is even irreducible in many cases because this is due to the noisiness of the training or testing data itself. And the only way to reduce this part of the error is to clean up the data. For example, you can fix the data sources such as broken sensors or detect and remove any outliers. So let's diagnose more about the underfitting and the overfitting problem. So as we have mentioned earlier, in the case of high bias, we will have a simpler model but a complex data set. On the other hand, if we have high variance, we will have a complex model but a simpler data set. So underfitting results in a large training error and there are high possibilities that the validation error will also be large and there is a high bias in the underfitting problems. On the other hand, if you have a more complex model, there is a small training error because you are able to model each peculiarity into the data set. However, when you test it onto the validation error, it is likely to have a larger value and it has high variance. But if you have just right amount of complexity that correctly represents the dataset, you will have small training error and even smaller validation error. So you can fix the underfitting and the overfitting problems whenever you encounter it in your training model. And these are quite prevalent phenomena and they occur frequently with each model implementation. So for example, if you have trained a slightly less complex model with respect to your data, you have the underfitting problem and you can fix it by getting more features of the training example. Increasing the amount of features can help your model to learn better about your data set. However, increasing the amount of examples will not likely to help the underfitting problems because your model is less complex with respect to the examples. The amount of examples will not have significant effect on the underfitting removal. However, you can improve or enhance the complexity of the classifier or the regressor. You can enhance its complexity. For example, if you're using a multi-layer perceptron model, you can try to enhance the hidden units. So on the other hand, if you run into an overfitting problem, this will mainly due to the fact that your data is less complex than the model you have chosen. So in this case, if you increase or enhance the data sets, for example, if you get more training examples, this might help. This may be the case because you may not have the all domain examples. There may be some misrepresentation, and when you enhance the training set, there are likely chances that your training examples meet with the complexity of your model. Or on the other hand, if that is not the case and increasing training example does not help to reduce the overfitting, you can try a smaller set of features. That means you can try to remove unnecessary features which your classifier or the regressor has learned. On the other hand, you can simply remove the or decrease the complexity of your model. For example, again, if you're using a multi-layer perceptron, you can try to reduce the hidden units. So remember again, you have to do it onto the validation set before trying the model onto the generalization uh, set or the test set. And the good news about the validation method is that it is very simple and you can achieve it easily. But there are some trade-offs that you have to bear when using these techniques. And one of the major hindrance is that it wastes some data. So in general, if you have the more data examples, we will have the better estimates and this will not have the effect onto the training or validation data proportion. So for example, if we have a smaller set of the data, we estimate parameters on 40% less data. That means we only train onto the 60% of the examples because 20% are removed for test and 20% are removed for the validation data. So if we have a small data set in our test or validation set, might just be lucky or unlucky, then you do not have an probable confirmation that you have trained your model effectively with respect to the model example or the training example or the test data. However, you can use the cross-validation technique, which is a method for performance evaluation that wastes less data with respect to the training, test, and validation method. So let's look into the details of cross-validation methods. So let's deal with the first problem, which is the small dataset problem. And let's say we have a small dataset represented again here in the graph. We have the features represented on the x side and the predictions presented on the y axis. So the data set is same for all three models, and we picked a simple model which is a linear model, and we picked a slightly complex model which is a quadratic model, and we picked an extremely complex model with which maps all of the training examples, and let's say we name it join the dots model. So it's just a name. So as we can see, we measured the training errors on these different different models. So as we can see, training examples are marked with the black dots, and the testing examples or the validation examples are marked with the green circles. So once you trained all of the three algorithms, you can see the training error on the first set is higher. Even in the second model, it is significantly greater, but in the third model, which correctly maps all of the training examples. So once you check it onto the validation dataset, which is marked in the green circle, you can see there is error into the first model. There is significantly or equally proportionally less error onto the second example, and there is significantly greater error than the second model onto the third model. So we measured the mean squared error, and we have three different uh, measurements. So as you can see, although our second model did not perform well onto the training example, it performed really well onto the testing examples. But still we have the problem of the small dataset. Therefore, we are unable to train the model onto whole set because of the deviance. So one of the technique to overcome such problems into the small dataset is using a leave one out cross validation technique. So in this technique, let's say we have number of examples, and for all examples we take from 1 to n. So let's take one example at a time. For example, x of k and y of k be the kth example. That means we have any one example picked from 1 to n, and we temporarily remove this example from the data set and then train the example onto the remaining examples. And once you have trained the model onto the remaining examples, then you note the error onto this particular removed example. And when you are done with the all points, you report the mean error, and the model with the lowest mean error will be the optimal choice model. Let's say we picked the same dataset with the different models, and we implemented the leave one out cross validation techniques onto the linear model, quadratic model, and join the data dots model. So we measured the mean square error using the same leave one out cross validation technique, and you can see in this case our quadratic model reported the lowest mean square error. Therefore, this optimal model will be selected for generalization onto the test cases. So now you have an option to choose by using a test set or a leave one out set, and both of the examples or both of the techniques have their upsides and downsides. For example, if you pick the traditional method of the model evaluation, such as dividing the dataset into the training, validation, and test set, you may have the advantages that it is a very cheap method, and you do not have to worry about deviance of the examples into the different set and repeating the training for a multiple or numerous time with respect to training data. But it may give unreliable estimates of future performance because the data may not correctly represent equal amount of distribution. On the other hand, leave one out is expensive, but it does not waste the data. As you have seen in the previous example, it only takes one example at a time and removes it from to the uh, data set and then train the model onto the remaining examples and then place the example back into the data set. So now we have two methods to measure the performance of our algorithm, but we can get best of the both worlds by employing. One way is to use the KFold cross validation technique, which particularly is designed for using cross validation with the same data. So in this technique, as the name suggests, the dataset is divided into different folds. So as you can see, the five-fold cross-validation is shown in this slide. So you have to make five different copies of the same training data. So the training data is represented in five different copies from 1 to 5, and in each copy you use 80% data for the training and 20% data for testing, which is marked in shaded area. However, you use a different set of testing data for each fold. So as you can see, in the first case you used lost 20% of the data, and in the second you use about examples from 60 to 80, and in the third you use 40 to 60, and in the fourth you used examples from 20 to 40, and in the first you use the first 20 percentage amount of examples from the training set. So in the each fold you train onto the training examples and test the error onto the testing examples. So again we have a similar model: linear regression, quadratic regression, and join the dots. And we have similar kind of data sets, and we have to make three copies because in this case we are using a three-fold cross validation. And for three-fold cross validation, you have to break the dataset into three partitions. So in this example, we have k is equal to three partitions colored in red, green, and blue. So for blue partition, train all of the points except the blue partition. Find the test set sum of errors on the blue points. That means train onto the green and the red points for the red model and test it onto the blue model. So in the second case, for the quadratic regression, again we have three sets, and for this case we have the green partition. So in this case we will train our model on all of the points which are not green, and then we will find the test set sum of errors on to the green points. And finally we have the red partition, and we will train on all points into the red partition and find the test sum of errors onto the red points. And then again report the mean error. So again the quadratic regression outperforms the rest of the models, and you can see mean square error on threefold is slightly less in quadratic regression than a complex model and a simple model. So again, cross-validation in terms of k-fold have positives and negatives as well. So for example, if you use a 10-fold cross-validation, that means division of the training examples into 10 subsets, you faced only about 10% of the data, and it is only 10 times more expensive than the leave one out training uh, method, which we discussed previously. However, there is a downside that it actually weighs about 10% of the data, and it is 10 times more expensive than the simple method because you have to test it 10 times. On the other hand, if you use lower value of the k for the threefold, and it is slightly better than the test set in terms of its error per error reporting, but it weighs about more data than the tenfold because you will have the 30% or the 33% of the data used for the testing phases, and it is more expensive than the test set. And if you used n-fold cross validation, therefore uh, it is picking up only one example randomly at a time, therefore it is identical to the leave one out method. So you can also use the cross validation for classification, and instead of computing the sum squared error on test set, you should compute the total number of misclassifications onto the test set. So cross validation facilitates in a number of ways for optimal model selection. For example, it can help you to choose number of neighbors in a k nearest neighbors algorithm. It can help you to choose kernel parameters for support vector machines. We will cover support vector machines in another lecture. So cross-validation facilitates in choosing which features to choose, and you can remove redundant or irrelevant features depending upon the cross-validation score, and it will help you to choose which classifier to use as well. So again, cross-validation based techniques are used to select the best model. So we are trying to decide which algorithm to use. So for example, let's say we are working on a particular data set and we use six different algorithms to train on to the training examples, and we want to decide which is the optimal model. So we will train each machine learning algorithm and make a table like this. So we will report the training error for each model, and then we will report the tenfold cross validation error. So we can compare two different errors. As you can see, training error is slightly less on to first and last few algorithms, but when we compare it using the tenfold cross validation error, just because our data is less predictable and have lower amount of examples, we come to know that the third classifier performs much better onto the tenfold cross validation error. Therefore, this is our choice of the model. So another example is shown here to choose the number of nearest neighbors for a k nearest neighbors algorithm, and this is our regression task. So in the first step, you compute the leave one out cross validation error for six different model classes. Remember, you will choose leave one out cross validation when the amount of data is limited. So we choose the algorithm depending upon the different parameters, and we reported the training error in terms of tenfold cross validation error. So the second step is to choose the model that gives the best CV score, and in this case we have k is equal to 4, which reports lowest CV error. So train with all of the data, and that's the final model you will use. So you may wonder why we have stopped at k is equal to 6. Well, to be honest, there is no good reason, except that it looked like things were not getting better. Instead, there was the pattern into the cross-validation error, which was significantly greater than the previous k. So we will prefer that the amount of error provided on a significant amount of training algorithms is quite sufficient for us to choose an optimal model. But are we guaranteed that this optimal model of K versus the leave one out cross validation will be the global optimal, the best solution? We cannot say for the sure, and in most cases it is not the case. In fact, the relationship can be very bumpy and you have to encounter different hyperparameters to choose best value. But what you can do is to make guess, and you should do if you are depressed at the expense of doing leave one out cross validation for k is equal to 1 through 1000, and you cannot have the enough computational power to test for each of the hyperparameters. You can try a different subset. For example, in the case of k nearest neighbor, you can use an exponential value, and you can start from 1 and then use 2, 4, 8, 16, 32, 64, and so on to different versions of up till 1000. And then once you have found the different optimal methods, for example, you have chosen a method which is between 64 to 128. That means the error increases till 64 and then it decreases from 64 to 128, and then it increases 128 onwards. And then you pick this subset and then do the hill climbing from the initial guess at this problem at the k, and then you can optimize the algorithm with respect to this subset. So there is some more concepts about cross-validation, and one of the significant one is the stratified version. For example, some datasets may require you to have equal proportion of examples in main training set and the subsets as well. So whether you choose the random sum sampling or KFold cross-validation or leave one out cross-validation technique, make sure each of the training or testing subset thus created always have the same proportion examples as the original set. So for example, let's say in our data set for an image classifier, we are predicting the types of animals, and let's say we have three different types of animals in our original data set. For example, cats, dogs, and bulls. So we stratified sampling ensures that whenever we divide our training set or test set, our subsets must contain same proportion of examples as the original set. So let's say our original set had 33% of examples for each representative class. So stratified versions ensure that your subsamples also contain 33% of each class representative. So this will help the KFold or the leave one out or even subsampling approach to work equally on the training examples and then make predictions with respect to proportionate testing examples, so that there is no sparsity between the example training subsets or test subsets. So you can also employ cross-validation with another paired approach, which is often referred as 5 cross 2 cross validation. So the concept is to divide the training examples into 10 subsets, and each are used in pairs. So let's, for example, we have a training set T, which is the original set of pre-classified examples. So the first task is to divide T randomly into two equally sized subsets. So then for each subset, repeat the division 5 times. That means each test training subset is further divided into 5 subsets. The result is 5 pairs of subsets denoted as Ti1 and Ti2, 1 to 5. So for each these pairs, use Ti1 for training and Ti2 for testing, and then other way round, use Ti2 for training and Ti1 for testing. Therefore, you will generate 10 training or testing sessions, and then you will calculate the mean value and the standard deviation for the chosen performance criterion, and you will choose the optimal model which performed well on these subdivisions. So this is the end of this lecture, and if you want to explore more about the topics discussed in this lecture, you can read some concluding topics of chapter 11 from Introduction to Machine Learning reference book, or you can read the selective topics about cross-validation in chapter 2 and 3 of Machine Learning hands-on reference book. Apart from that, reading material regarding the machine learning methodology is provided along with this lecture, and I will encourage you to go through the reading assignment lectures and then overview the practical aspects of the same approaches discussed in this lecture with the code file provided with the lecture as well. So if you have any further questions, you are encouraged to ask at any time. Thank you very much.